Let us solve another problem on Shannon Fano coding. The message ensemble is given here. So x is a random variable and there are 7 different messages x1, x2, x3 up till x7 with the probabilities as follows 0.4, 0.2, 0.12, so on and so forth. So now we need to apply the Shannon Fano coding procedure for this and find. After that we shall be finding the efficiency of the code. So I would write and find the efficiency of the code. So we start with the procedure. First we need to, as told, we need to ensure that all the messages are arranged in the decreasing order of their probabilities. And as you can see, all the messages are already arranged in decreasing order of their probabilities. So we have messages x1, x2, x3, x4, x5, x6, x7 and their corresponding probabilities p of xi. So we start to get the encoded message. So what is the procedure here is that if at all you see the sum of all these probabilities, then the answer will be 1. So the sum of all these probabilities would be 1. So if at all we take the summation of all these pxi, the answer would be 1. So I have to divide the probabilities in such a way that I would be partitioning all the messages into 2 groups. So how we shall partition them? It is not possible to have equal groups of say 0.5 and 0.5. So I will partition them as 0.4 and if this is 0.4 then this entire what is remaining will become 0.6. So it's not possible now 1 can be divided into 2 equal parts when it is 0.5 and 0.5. But that will not work out. So what we shall be doing is that we shall be dividing into 2 equal parts, more or less equal. So either I can take this 0.6 and this will become 0.4 or I can take 0.4 and 0.6. So there are 2 different ways of partitioning, 2 different ways I can partition in which 0.6 plus 0.4 plus 0.4 is equal to 1. Also 0.4 plus 0.6 is equal to 1. So 2 ways of partitioning are there. So I can use any one of these ways to partition the data. So I shall be doing both and checking which one is a better way. So sometimes you could be asked to partition in 2 different ways and then compare the results. So first what we shall do is that we shall have the partitioning done here. So I shall partition here. So that this particular data which is there is 0.6 and this if at all you add and check it will become 0.4. So how to encode the message now? In order to start with the encoding procedure, so what we do is that above the line which we have drawn we shall be assigning bit 0 and below the line which is drawn I will be assigning bits 1. So here it would be 1, 1, 1, 1, 1. So 5 bits, 5 messages are below the partition, 2 messages are above the partition. Now this whatever is above the partition has to be again partitioned and whatever is below this line has to be again partitioned. So how we would be partitioning this one? It is very simple. There is no option. There are 2 different messages. And if at all you want to partition them into 2, definitely you have to separate them out. And what bit will I assign here? The top one I will assign a 0 and down I will assign a 1. Similarly, this group of messages which was down, whose sum was 0.4, I have to divide it again into 2 groups. So how do I divide it? If at all I see the sum is 0.4, so 0.4, 50% is 0.2 and 0.2. So the best possible combination is 0.12 and sorry, this is not 0.18, it is 0.08. Mistake. So I can combine 0.12 and 0.08 because that would sum up to 0.2, and this whatever is below 0.08, 0.08 and 0.4, this will also sum up to 0.2. So I would be partitioning. Where would be the line of partitioning? Line of partition would be here in the middle. Fine. So after having partitioned this, what I would assign is that below would be 1 and above would be 0. So above the partition line I have assigned 0, 0, and below it is 1, 1, 1. Now still further we have to partition. Still further we have to partition these groups. So this one is complete. The top one is complete. You need not further partition this. But this below you can still partition this further. That is, what you can partition further is these two groups. So I can partition this group and I can further partition this group. So we have to go on partitioning till all of them will be like, all of them will have a different message, different encoded message. All the messages will have a different encoded message. So I can partition this because there are two different messages. I can simply partition by drawing this line, and above that I would be assigning it as a 0 and below I will be assigning it as a 1. And what happens here is that the sum of these probabilities is how much? 0.08, 0.08 and 0.04. So it is 0.2. Now 0.2, if at all I have to divide by 2, either I can have a partitioning line here or I can have a partitioning line here. So which one would we prefer? We would prefer this particular line, whatever I have retained, because if at all I do this, one side I will get 0.08 and other side I will get 0.12. Whereas if at all I had to select a line here, I would have got 0.16 here and 0.04. So which is not equal partitioning. Okay. So that is the reason we are not selecting this line. We are going to select this line for partitioning. So I would be drawing this line here, and above this bit we would be assigning it as a 0 and below it would be assigned as 1. Now still we are not done with the partitioning process. We are still having the last two messages to be partitioned, and the last two messages could be easily partitioned because there are only two of those messages. So I can just draw a line here and I can partition it and I can give it 0 and 1. So this is finally we are done with the partitioning of the message. So finally we are done with this procedure of partitioning. So what we write is that whatever code we have got here, we shall write that code once again. So the first message will be encoded by using 00, second message X2 will be encoded by using 01, third message 100, fourth message 101, fifth message 110, 1110, 1111. So if at all you see, no two messages here will have the same code. Everybody's code will be different. Each message will be encoded in a different way. And one more thing which you can observe here is that the messages which have a higher probability are assigned lesser number of bits, and the messages which have a lower probability are assigned more number of bits. So that is what you can notice. So what we next find out is that we find out the length of the code. So this length is nothing but Ni. So length of the code is nothing but how many bits are assigned to each of them, each of the message. So what you can do is that 2 bits, 2 bits, 3 bits, 3 bits, 3 bits, 4 bits, 4 bits. Similarly, we can find out log to the base 2 or 1 upon p of xi. What is this? What we are finding? This log to the base 2 1 upon p of xi is nothing but information. So I am finding the information of each of these messages. So I can find out, and I want you all to calculate this. You just have to take log to the base 2 of 1 upon 0.4 and things like that. So you can just calculate it. You can pause the video and calculate it on your own. So these are what answers which I have got. So we are getting this approximately. So what you can see is that the one who has, this is not a very efficient coding scheme, because the one which has got the same information, say same information of 3.64 and 3.64, one I have assigned 3 bits, one I have assigned 4 bits. So if at all you see here, both x5 and x6 are going to have the same probabilities. So because they have the same probabilities, they will be amounting to same amount of information. So but what happens is that both of them carry equal amount of information, but one of them is coded by using 3 bits, one of them is coded by using 4 bits. So this is not a very efficient technique, but yes, we cannot, this is because of the improper partitioning, because it is not, whenever you are dividing into 2 and the last 2 messages are left or something like that, and one's probability is more, another one's probability is less. So you cannot have a equal division which is possible. So that is the reason you are getting this particular problem. Now the next step is we need to find the efficiency of the code. And in order to find the efficiency of code, first we shall be finding h of x. So I want all of you all to calculate h of x. This is the exercise which we have been doing. And then you all need to calculate L1, that is the average length of the message. So L, I am using it as L1 because I will be again showing you a different procedure for encoding. Okay, and we shall encode it in a slight different way and then check what will be L1. So average length is nothing but summation of I is equal to 1 to m p of x into, sorry, this length you indicated as not ni but li. Some books they use L, some books they use N. So I want you all to find out these both, and then after finding these I want you all to find out the efficiency of the code. Now once again we shall be going to the second procedure of encoding the messages. So we take a different partitioning method. Now what we had done previously is that we had partitioned them here. So this was considered as 0.6 and this was considered as 0.4 and we had partitioned. Now I changed the idea, and what I would do is that I would partition here. So here on top I will get 0.4 and this entirely would become 0.6. So let's go ahead with this. So when I do the partitioning here, I would like to extend this line, and on top I will be assigning a bit 0 and rest all I would be assigning bits 1. So we are done with first stage here. Now on top it is completely done because there is only single message which is remaining. Now below, when it was say 0.6, okay, this total was 0.6. So I need to divide it into 2 parts. So when I divide it into 2 parts, definitely I would take the partitioning line here, because this on top would be 0.2 plus 0.12, that is 0.32, and left will be 0.28. So I would be taking this division line here, and on top I would be again assigning 0, 0, and below I will be assigning 1, 1, 1, 1. So on top part, if at all you see, there are 2 messages, and those 2 messages are 0.2 and 0.12. Although they are not equal, but you have no other option left other than assigning a 0 and a 1 and to partition them and to separate them so that this part is complete. Now the next one below, we have 1, 1, 1, 1. So I can combine it as either these 2 and these 2, I think that is the only option which is available, otherwise it would be too much. So this total probability below, if at all you see the total probability below this entire thing is nothing but 0.28, and 0.28 has to be divided into 2. So how it is done is that I will divide this as, and this will become 0.16 and this will become 0.12. So approximately they are equal, they are not exactly equal, but yet. So I have the partitioning line being drawn here, and below it is 1, above it is 0. So again we are on in this top part we are just left with 2 bits, and below also we are left with 2 bits. So we cannot do much directly, blindly we can divide it into this way. So we are done with the coding procedure. So we write the codes. Okay, so then we write the lengths. And log to the base 2 1 upon p of xi, it is the same thing what we had got previously. It is the same thing what we had got previously, so I'll just write again. Now what I want you all to do here is that I want you all to find again h of x and L2 bar. h of x will be the same for both, whatever type of partitioning technique you use, but h of x is found from p of xi. So p of xi is the same. So h of x will be the same. So what will change is that in both these techniques the efficiency will decrease. In one of the case the efficiency will be less, in another case efficiency will be more. So what happens is that I want you to compare both these techniques. Okay, I want you to compare both these techniques and then find out the efficiency in both. So depending upon what is the efficiency, whichever efficiency is higher, then that would be the better efficiency, better code. I am giving you the task to find out h of x. You have to find, I have shown you 2 methods. So for method 1 and method 2, you need to find h of x. Here also you need to find h of x. h of x would be the same. Then you have to find L1 bar, L2 bar, and then you have to find efficiency 1, efficiency 2. Now what is the equation for efficiency is nothing but h of x upon L bar into 100%. Now here obviously that log to the base 2 of d would be there, but we are grouping using 2 bits, so it would be log the base 2 of 2 would be nothing but 1. So whichever has the higher efficiency, that code would be the better code. Now after solving these 2 problems, I would just like to comment on certain things. Now in the first case, when we do the first problem, if at all you saw that we could equally divide those groups. The messages were such that we could have in both the groups, whenever we divide the probabilities in 2 groups, the probabilities of one group and the second group were exactly the same. Okay, so in that case, if at all we had when we did the grouping and the coding coding efficiency was 100%. So why it was 100% is that because the groups, we had properly divided the messages into equal groups. But when we took this example here, it was not possible for us to group them into exactly equal groups. Okay, first case only we were getting 0.4 and 0.6, meaning one group was lesser than the other group. So however you do the partitioning in both these cases, you will observe that efficiency will not come equal to 100%, because in the first partitioning itself we are not able to divide it into equal groups, and obviously in the later partitions also we were not able to divide it into equal probability groups. And that is the reason whenever we are not dividing them into equal probability groups, the efficiency would be reduced. So it is not that we are reducing the efficiency, but the messages are only such that the probability of occurrence of the messages is such that it cannot yield 100% efficiency. but whichever gives the best efficiency, we have to take that, and that code will be the best code.